We now introduce a more complex or more complicated differential equation, the logistic growth equation. In this differential equation, it's actually one we've seen before when we were looking at the word models. We have a rate of change that's proportional to a current population and then the difference between L minus P. Now, we're going to put this in the context here of a bacterial culture that cannot be supported once the population reaches L. That's based on food supply or waste generation. There's some maximum population that can be sustained. And P is the current population. So in all of our study here, both K and L are going to be constants, and P's change with time. That's why it makes sense to talk about the rate of change of P. Now, if we look at this, it's a standard differential equation, and what can we say about some key ingredients here, about key points? Again, derivatives are most interesting when they're zero, or very small or very large. Let's take a look at this expression here. If P equals zero, then this whole thing is zero, right? Then we get derivative equals zero. The other interesting point is when P is equal to L. Then L minus P equals zero, which again means our rate of growth is going to equal zero. When does this become largest? Well, this is a little trickier, and here's where you start getting into more sophisticated logic. Yeah, let's write it out like this. If we're looking at this function here, ignore the fact that it's a derivative. Let's just focus on the right-hand side. What is this really? Well, it's a quadratic with roots at 0. And, well, we actually just saw, it also has a root when P equals L. So if we were just to graph this thing, and let's call it Z equals, we would have a quadratic that opens down, because it's LP minus P squared, so it opens down. L and 0, that's P. So if my population was 0, I would get a 0 derivative, or let's call this value here Z for the moment, I'd get a 0 value. If P is equal to L, the other end, I also get a 0. And because it's a parabola, it's going to be symmetric between those 2 points. And so the maximum Z value here would occur at P is halfway between 0 and L over 2. Now, that answers our 0 and largest. The smallest, well, we can see it goes negative afterwards. So Z negative outside that interval 0 to L. And I know, for some of you this is a struggle just because we have no numbers whatsoever. Don't worry about that. Just focus on the basic properties that we're looking at here, which is that this is a quadratic, it has a certain shape. We don't need to know what all these numbers are yet to be able to generate a general graph. Now, let's sketch the slope field associated with this differential equation. So remember, we just did a study for Z here, but we're now going to interpret that as slopes on the P versus T graph. So T is here, our population is here. How does our population change? What's the rate of change? What's the slope on this graph if we had this right-hand side? Well, we just said if population is 0, we get 0 slopes. So we can do a slope field there. And in fact, that gives us a solution immediately. And let's do those in black. That if the population starts at 0, it stays at 0. Now, that is not a very interesting model, but it's nice to see that. We expect that kind of behavior. If I have nothing, if I have no species reproducing, splitting, whatever, then the population stays at 0 forever. Where does it get more interesting? Well, it gets more interesting when we go up to this L population. We said when the population was equal to L, then I plug that into here, I look at those points, and I get a derivative of 0. So here we get that same statement, that if the population starts at a certain value, this time it's 0, or sorry, it's L, then it's going to stay at L forever. So if we're at our maximum sustainable population, we're going to maintain that population. And that's going to be, again, not an unreasonable thing. If we have that's what maximum sustainable population would indicate. Now, L over 2 came up earlier. At L over 2, Z, or what we called Z earlier, was largest. Or, well, Z was just dp dt, and so that was largest. And that translates to the slopes of P of t are going to be steepest in the positive direction. So if we look along this line, we're going to get positive slopes. We don't know how steep it is exactly, but we know it's going to be steepest there. Steepest compared to what? Well, compared to other population levels. We know it's going to be less steep further down. When P is at L over 2, we get a nice balance, we get a maximum slope. Everywhere else, we get less steep. And these should all be the same steepness. I'll try to correct that a little bit. There we go. With that in mind, this gives us a chance to explore what the solutions might look like. Let's say we started here. There's an initial population close to the maximum. We expect to have the population grow, but what would happen in between? Well, as we get closer to L, let's flip back a page. As our population gets closer to L, Z, which is our rate of change, gets closer to 0. So as we get closer, our slopes are getting closer to 0 as well. Actually, that happened down at the bottom end as well. We expect to have fairly flat, not steep slopes down near the bottom. And if that's the case, we're going to see a curve that probably looks asymptotic. We need more study to do that. But if we start close to the limiting population, the population is going to increase towards it as if it was going to stabilize at population L, at the natural limit. If we started at L over 2, we'd grow steeply and then do the same thing. Where it gets more interesting is when we start down with a low population. Let's start right down here. Every time we hit one of these lines, we should be going at the slope dictated by them. Ah, lovely. If we start with a small population, what do we see initially? We see initially something that looks like it might be growing exponentially. So we see fast growth because we're nowhere near the limits on the population. But then as the population reaches this transition point, here it's L over 2, we see the rate of growth slowing down, and again we move up towards the limiting population L and get there more slowly and slowly as time goes on. All of that is being derived from this differential equation, and this model, I would argue, is one of the most important ones in biology because it captures so much of the basic population growth that we believe is the case. Our old models have been simply exponential growth. We know that's unsustainable. This simple modification to an exponential growth model captures the idea of limiting environmental factors while still allowing exponential-like growth for small populations that are much further down, much lower than the limiting population. And we've seen people try to model human population on the Earth with these kinds of models and trying to match the values of K and L to try to predict what the maximum sustainable population on the Earth is. You also see it for other species as well. Anyway, so this is a fantastic model, and you have all the tools in your toolkit already to do the analysis that we just performed here. At the heart of it is understanding that you're given the rate of change of the population as a function of the population itself, and that these rates of change can be sketched out as slope lines, leading to understanding of what the right-hand side predicts in terms of the overall population over time.